Good afternoon to everyone. I welcome all of you to the 96th lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University with the support from RUSA 2.0. It is my pleasure to introduce today's speaker, Professor Mahendra K. Verma. Professor Verma is basically an engineer. He did his B.Tech in IIT Madras and switched over to physics and got his PhD from the University of Maryland, College Park, USA in the year 1994. He then started his teaching career as a visiting faculty in Department of Physics at IIT Kanpur in the year 1994. He is currently serving in the same institute as a professor. He also served as a visiting scientist in the University Libre de Brussels, Belgium, for an year in 2007. He was the Sanjay Mittal Chair Professor during the period 2019 to 2022. Professor Verma has received many awards for his outstanding career. To name a few, I cite the following. He is the recipient of Swarna Jayanti Fellowship from DST in the year 2006. He received the INSA Teachers Award in 2016 and Dr. Abdul Kalam Kray HPC Award in the year 2018. He is a fellow of INSA, Indian Academy of Sciences, and National Academy of Sciences. He is a fellow of all three Academy of Sciences. He is also a member of Indian Physical Society, Indian Association of Physics, and Plasma Society of India. He is a member of the Division of Plasma Physics of the Association of Asia Pacific Physical Societies and member of the Scientific Committee of Group D Research International Dynamo. He was an associate of the International Center for Theoretical Physics, Trieste, Italy, during the year 2004 to 2009, and was also the member of Program Advisory Committee of Science and Engineering Research Board, India, during the year 2012 to 15. Professor Verma has several notable publications in his area of expertise. He has given several lectures and talks in many conferences across the world. He has research collaborations with the top universities in India and internationally. During his career, he has guided several PhD theses and has mentored many postdoctoral fellows. He has written 5 books and has authored 188 publications in peer-reviewed journals and 27 conference proceedings and has a H index of 31. With this short introduction, now I invite Professor Verma to deliver his lecture. Over to you, Professor.
Thank you, Professor Santevellan. It's a nice, it's a great pleasure to talk in this nice forum. There are many students and I see some colleagues whom I know. So thanks for coming in this hot summer. Where I am right now is quite hot, but thanks for coming. Okay, so let me talk about today's topic. Okay, let me put a full screen.
Yeah.
It's visible now, full screen?
Yes,
yeah.
Full screen.
So my cursor also is tiny, but yeah, so I'll use the cursor.
We are able to see. Yes.
Yeah. So physical laws in complex multi-scale world, lessons from hydrodynamics. So I think there are something important and new in this line of thought. Though this multi-scale phenomena is talked about for 100 years or so, but let me just try to give some introduction and then some new results which came out in last 3-4 years. So these are the books which Professor Sandevalan was talking about. I like to write this such stuff because I think they are helpful to students to get an idea about the subject. So, for example, this book has quite a bit of what I'm talking about today. Okay, so multi-scale world. Is very easy to see that our universe has multi-scales. Multi-scale is many length scales. Okay, that is what multi-scale is. So we start from quarks, which is 10 power minus 15 meters. Or even shorter, sorry, nucleus is 10 power 15 meters, but quarks are even smaller. Okay, so nucleus is somewhere here, protons and neutrons. Then we get to atoms, and then we get to cells, humans. So these are physics world, atomic world of physics. Okay, physics world is a lot of it encompasses huge scales, but after this microscopic description of quantum physics, we come to biology, and then we get to planets and sun and stars and so on, solar system, and then we reach galaxy and universe. So this part is biology, of course, but then where there is physics too in that biology, but this part is to physics. So we deal with huge length scales. Now, if we look at description of stars, here too, in a star, in the atmospheric of a star or of the atmosphere of the Earth, we have scales ranging from meters to kilometers, and we need to describe all of them simultaneously, okay, at the same time. And that's in fluid mechanics, we do that. So that is multiscale. Within a system, like we can look at the sun or Earth, we have multiscale atmosphere. Okay, and if you look at molecules too, that too is multiscale in some sense, because we go from angstrom to micro. So if you give big molecule like polymer, then we get from angstrom to micrometers. Okay, anyway, this is a phenomena, and let's see, we'll discuss only one aspect of it, which is fluid mechanics. Okay, that's what I'm going to focus on, connected to fluid mechanics. Okay, and so let me just make some philosophical remark. So the dominant paradigm, though there are alternative paradigms like holistic explanation of phenomena, but often we go to this reductionist paradigm, where we say, well, if we understand atoms, then we can understand molecules and polymers and so on, and bigger stuff, right? So that's what is the focus on reductionist approach. For example, we say, well, if you understand Newton's law, then you can understand the whole world. Newton's law of particles, okay? So this is what is called reductionist paradigm. You can reduce the system to the most fundamental or most smallest scale, and then you formulate laws for smaller scale, and then conjecture that we can understand the global phenomena based on this. This is called fundamental laws can explain everything. And if you look at this world called theory of everything in particle physics or string theory, this is the thing, that if you understand basic particle phenomenology, then you can, in principle, explain the world. The word is in principle, that's a problem. Okay, so no, my point, well, I'm not the first person to say it. There are various papers and so on, which I'm going to cite in the next slide, that laws are at different scales. For example, biology has its own laws, like law of natural selection. Now, there may be people who may say, well, we can explain law of natural selection based on quantum physics. Well, I'm not a believer of such assumption, but I would say there are laws at all scales. So laws are at different levels. This is some kind of conjecture, okay? And of course, in terms of belief system. So, so there are levels. For example, we have particle physics. There are Schrodinger equation in principle. Then we go to kinetic theory, which is involving many particles. And you know that equation for kinetic theory, like Boltzmann equation, is different. Though it is derived from Newton's laws and the Schrodinger equation, but kinetic theory is in some sense is a different equations which we deal with. Hydrodynamics goes on top of it, and then climate and astrophysics. So there are equations as well as phenomena. For example, global warming. Is it possible to explain global warming from Schrodinger equation? I mean, I think it's even, well, it's not possible. I mean, that's my straight away take on it. And we can go to another set of multi-scale or multi-laws. So we have atoms and molecules. Then we go to cells, which is basically deals with biology. It's a complex system. Of course, there are physics involved in this. Then organs have their own behavior. Like for heart, we think of how heart works without resorting to microscopic description. Then we have body and mind. So mind is psychology, you know. So that's the multi levels and multi laws. That's what I would like to say, that we should think in this manner to explain multi-scale phenomena. Now, these are some references. Some of these papers are very, very famous, like More is Different. This is by Phil Anderson. And he's telling that this broken symmetry in condensed matter physics, like phase transition involves broken symmetry from water to liquid. You know, there is a, from gas to liquid, there is a symmetry changes, and that is not explainable purely from purely from microscopic description. Broken symmetry itself is a fundamental description of nature, but that's at a different level. And there's a nice paper by Laughlin, which is equally important, a theory of everything. Okay, but he's criticizing theory of everything from particle physics point of view. Now, I try to kind of provide similar description for hydrodynamics. So you can start from kinetic theory, and there's a description, and then hydrodynamic description, and there are contrasts, there are differences. Well, this is about this paper, and there's a very short paper where I try to talk about multi-laws. So this is just a reference. Now let's get to the topic. So that was philosophy, okay? In some sense, I'm just stating some larger principles. And we use multiscale in hydrodynamics, and that is what I'm trying to relate it to microscopic description of nature. So actually not only students, I think if you talk to some colleagues, they may not have very clear perspective of single scale versus multiscale. This is of course very natural in fluid mechanics, but let's look at, let's contrast it using some examples. And there are associated phenomena, okay? And some of it is shocking. I hope it is shocking. So single scale physics, crystal is an example where there is a smallest scale which is recurring, right? The distance between basically between two molecules or two atoms. This is the scale for crystals, lattice spacing, which is called. Now, here I'm talking about sugar cube dispersing, sugar molecules mixing in water. Okay. Now we have sugar molecules which is mixing slowly. So right now I'm not stirring the water. Water is still, and the sugar molecules are moving around. And that description is well known. This is by Brownian motion by a scientist called Brown, first discovered or first propounded by him. And the idea is that the sugar molecules collide with water molecules and they get scattered, or they basically diffuse in the system, and that's how sugar is spread all over the system. Now, what is the length scale for this system? Is a mean free path length for this system. In fact, there's only one scale, which is mean free path length, okay, which is collision distance between sugar molecule with water or water with water. Okay, that's description. And what is the speed in this? It's a sound speed. That is the speed of these molecules in this medium. And there's a time scale, is length by sound speed. Okay, so there is one scale. This is the scale for Brownian motion. Okay, please keep in mind the scales, which we're gonna see this in several slides in future. Now, this is by picture taken by Perrin. Okay, book by Perrin. So this is the molecule. So this experiment was done by Brown, and he is looking through a microscope the movement of pollen in water beaker. Okay, so water is still, and the pollen particles are moving in this liquid, and that is, of course, there was no computer at that time, so he is doing by looking at it, and by his hand he is drawing this what he sees with his eyes. Okay, so pretty difficult things they used to do in the past. Things are automated now, but this is a picture, and you can see that this mean free path length essentially for the pollen with water, okay, a single scale. Now we can see how it disperses. So I wrote a simple Python code, and x-axis is number of collisions, and y-axis is, so this is not for pollen basically, but it is for a random walker in one dimension. Okay, so random walker in one dimension, we know that if it is the random walker can take one step in the right or one step in the left, but if you allow the person to take n steps, so it won't be, the distance travel is not n, right? Because sometimes the person is going to the left or going to the right. So it is known, I mean, this can be derived, that the distance traveled is square root n. Okay, and if you say that, well, n is proportional to the time elapsed or time taken, it's a square root of t. Okay, so this is very well known. I mean, this is part of BSc physics in statistical physics, or even school days. I think this is part of syllabus now. But you can see that the dashed line is square root of n. Okay, and it is, in fact, there are different examples, and they're just telling you that, well, some are more than square root n, but on the whole they follow square root n law. Now, so that is for diffusion of pollen. Okay, now the question is heat. Well, right now we are trying to cool in the summer heat in most places. So the cold temperature from air conditioner, does it follow the Brownian law, that motion which I described? So if the cold wind is starting from the lid of the air conditioner, how long will it take for it to reach me when I'm, let's say, 1 meter away? Okay, so let's try to estimate it. So this is the talk. I wrote heat that time, but we can, heat and cold are basically the same equation is governed by, which is diffusion equation. So theta is the temperature. So this partial temperature, partial T, is kappa grad squared theta. Okay, theta is temperature and is Laplacian. Kappa is the diffusion coefficient. Now, just doing dimensional analysis or just estimate. So temperature by time. So time is time taken to traverse distance L. Okay, so as I said, I am 1 meter away from the air conditioner, so L will be 1 meter. Okay, and now this time is time taken for the cold wind to come to me, okay, to give me some comfort. So so this theta will cancel, and we get L equal 1 meter. Kappa we can check for air. It is around, is approximately is 10 power minus 5 meters square per second. This is for normal temperature. STP is called standard pressure and temperature. So that will give me time, right? From here, time will be L squared by kappa. So you just get from here, which is inverse of L squared is 1, and divided by 10 power minus 5, which is 10 power 5 seconds, which is 3 hours. Look, this makes it terrible, right? I mean, I can't wait for 3 hours for air conditioned cold air to come to me. So there's something has gone wrong. By the way, this is not only atmosphere, this air conditioned cold air, it's also true for perfume. No, if I put perfume in my face, I cannot wait for 3 hours for perfume to diffuse. It's simply, I mean, this of course doesn't happen, but there is a fallacy, right? There is a problem. Now, where is the problem? That's where fluid mechanics comes into play. For atmosphere, or for room in my, for the atmosphere in my room, this is not the correct law. This is definitely not correct. What is missing is the velocity of the wind, okay, which is coming from the atmosphere and hitting me. Okay, that is the missing piece. Now, how to incorporate it? By the way, this is not the molecular motion. In fact, it's there in textbook of school. I've seen it. That they say, well, this dust particle which is moving in my room, it is because of Brownian motion. Is getting collided by molecules of the room. Well, molecules of nitrogen and oxygen. Simply incorrect. What is happening there is we have bunch of these particles together form a velocity. Okay? And that velocity is different than the sound speed. Like atmospheric wind or the the wind in my room, the speed is around 1 meter per second, okay? Not more. Well, it would be few meters per second, but it is not 300 meters per second, which is sound speed. Why? Because within that parcel, like let's say I take 1 cubic centimeter of air, there are cancellations of the speeds of the molecules, and the mean speed or the local speed of the wind is around 1 meter per second. Or you might see in weather reports that atmosphere in normal atmospheric wind is around few kilometers per hour, 10 kilometers per hour. Well, of course, unfortunate cyclone which is moving in Bay of Bengal, that could be going with few hundred kilometers per hour. But typical speed is 10 kilometers per hour, which is much less than sound speed. Okay, and that is a hydrodynamics. Okay, so that is not a molecular picture; it's a collective picture. Okay, and that is multiscale. Okay, so the wind I'm seeing it here. It is collective motion of lot of molecules, and that has its own physics. Okay, you can see that I'm contrasting diffusion equation with Navier-Stokes equation, and there's some thing which you cannot, well, you can derive it in principle, but it's better to just evoke a hydrodynamic picture. So I'm just going to give you a brief introduction to turbulence, okay? Because I need it for describing the fluid motion in near air conditioner. Okay? So here we have this large vortex. In fact, this ocean, this is a real picture, a large vortex, and that vortex breaks into smaller vortex by nonlinear interaction, which is in hydrodynamics, I'm sure many students know about it, is U dot rad U. So that term breaks this vortex into several smaller vortex, that breaks into further smaller vortex, and finally to very, very tiny vortex. And so in the atmosphere, this could be, for example, few centimeters, okay, the scale. Or in a coffee cup, if you stir a coffee, then this speed, the scale at the scale is, I mean, at tiny scale is around micrometers. Okay? And below the micrometers is kinetic theory, where we have molecules. Okay? So this picture is described by hydrodynamics. U dot rad U. We can define velocity of a collection of molecules with velocity vector U, which is continuum. Okay? And this part is, this description is hydrodynamics. If you give enough energy, then it becomes turbulent. It has a large Reynolds number, and nonlinear term is very important. And this part is non-equilibrium. Okay, this part, and this part is equilibrium physics, quasi-equilibrium, because there is some heat coming into molecules, but this part is quasi-equilibrium. Now, so let me just show you a picture. In convection, thermal convection, what happens? There's a nice movie. We are seeing this vortex. You see, the talking about vortex is two-dimensional convection, hot below, cold above, and this interaction leads to change of vortex, merger, and so on. Anyway, let's not get into it, but this is what happens in a lot of atmospheric phenomena. So there's a famous theory of turbulence by Kolmogorov. This is in 1941. Kolmogorov wrote certain laws for turbulent flows. So the idea of Kolmogorov is that energy goes from large scale to small scale. See, this is multi-scale now. So in coffee cup, my spoon stirring, that scale is around 10 centimeter, and that is going to, from 10 centimeter go to 1 centimeter, 1 centimeter to 1 millimeter, and so on. So it keeps going down to around micrometer, and that cascade, this is called cascade. So here x-axis is the wave number. Okay, wave number is inverse length. Okay, 1 by length, and it turns out it has been observed in experiments too that energy cascade, energy going across scales. Okay, now this is a pretty interesting thing. This is not the normal flux, which is energy passing through a surface per unit time, per unit area. It is not that. It is energy going from one scale to the next scale. Okay? and that energy going from one scale to next scale is constant. So this constant flux, which is pi k, is epsilon u. So let me just give an example, which I think is a fun, nice example. So what is multiscale energy flux? So of course, India is one nation, so we have central government in Delhi, and that gives money that has central budget, and that's supposed to go to different states. So money goes from center to states. It is a very simplistic picture, but it will give you an idea about flux. Okay, that's what I'm trying to say. Of course, you may say, well, some states are also sending money to the state center. Okay, I mean, I'm not getting into that aspect as well as politics, but let's say the energy is going from the center to the states, and then to states it goes to district. It is not really flowing in a real space. Money is of course going through electronics or through banks, but you can see that how much money is going from center to states. And there is you can make a circle, and from that scale center to states. Now from states to districts, there are many districts, and that's another scale of energy transfer or money transfer. From districts to villages, so that's another energy transfer. So this is how the flow happens in turbulence too. So we have structures with a big structures, small structures, and so on. It is not connected with energy flowing per unit time, per unit area. Okay, that is not. This is a multi-scale transfer, which happens all the time in nature. For example, in earthquakes, there is energy flowing from large-scale tectonic plates to smaller scales. Okay, and that's what we see. So this flux, y-axis is flux, is going constant flux here. Now, as a result, is a bit of algebra here. Then we can show by dimensional analysis that energy spectrum, which is energy related energy at different scales. Now, since it is a multi-scale phenomena, I need to know how much energy is at different scales. And so we have energy at different scale, which is k minus phi-third. Okay, this famous phi-third law, and this dissipation rate is coming here. So this energy spectrum in the inertial range, which is called intermediate range, is epsilon u to the power 2/3, which is the flux, k minus phi-third. And this has been seen in many experiments, many simulations of hydrodynamics. Now we can use this law to derive the heat flow from the conditioner, air conditioner. Okay, now let's see how to do it. So from this law, I mean, of course I can't do it right now, but you can easily do this part by some simple algebra. Students can do this part. So it turns out we can derive velocity at different scales from Kolmogorov law. Velocity at scale r. R is the distance, or you can think of r is the vortex size. Okay, so there are different vortices. So what is the velocity at vortex size r, which is r to the 1/3, epsilon u to the 1/3. The same epsilon, heat flux. Okay, now you can see that velocity is not same at different scale. Velocity increases with scales. At small scale, there is a less velocity. At large scale, there is large velocity. It's unlike the velocity in a kinetic theory or Boltzmann gas, which is same velocity, which is sound speed. With some fluctuation, but sound speed is a single velocity scale. So you got multi-scale velocity, which is different at different scales. Now, we can find the time scale. Time is r by ur, and this is a different scale. We just plug this formula. Time is r to the 2/3, epsilon u 1/3. Now I can invert it. I can find r is a function of time, and r is t to the power 3/2. So it turns out the diffusion in atmosphere goes like this law, t to the power 3/2. The Kolmogorov theory works for fluid mechanics and turbulence, and diffusion is not square root t. Please remember, for kinetic theory, the diffusion is square root t, but here it is t to the power 3/2. Is very fast. Okay. Now, if you dig deeper, you will find that this is faster than ballistic. Okay. Somebody going this random walker, if he's sane, if he's not drunk, then the guy will go straight in a straight line, and the distance traveled will be t, right? It's same constant velocity, but this is going faster than t. And this is because of this velocity is different at different scale. And this what happens in atmosphere, and this is called Taylor diffusion. Okay, I should have written this name of the scientist who propounded, who gave this law. It's called Taylor diffusion, and this is what happens in the atmosphere. Okay, and okay, let's try to estimate after this. So, what the Taylor diffusion is very different than normal diffusion. Okay? Now, I want to give an example. Okay, now the two sisters traveling from, so you can replace Pune by Trichy. So this talk was given in CNSD in Pune. So I should replace Pune by Trichy. So so there are two sisters which are going from Pune to New York. Oh, sorry, one is going to New York, one going to Paris. Okay? So the first sister, first girl, goes from village A, same village, to Pune. Okay, goes, well, first we can go by train, as he goes by bus actually. Let's call this as a bus. First travel is by bus. Then Pune to Mumbai by train, and Mumbai to New York by flight. Okay, now you can see the velocity is increasing, right? From bus speed is lower than the train speed. Well, super fast train speed. Okay, and then we get to flight. The second sister, she goes from village bus, well, basically from the house to Pune by bus. But okay, so here they may go together, or she goes to some other. Okay, so this is the bus. Then this is a train, Pune to Delhi. So we are sending the other girl to Delhi, and from Delhi to Paris. Now I can see the distance between with function of time is increasing with time, right? I mean, Mumbai, Pune, Delhi distance is more in compared to the first distance by bus travel. Then New York to Paris is even more. So the distance is increasing with time, like, well, not to 3.5, of course, it depends on the speed. So this is a multi-scale phenomenon, okay? And that is what precisely happens in the atmosphere. Okay? Now, diffusion of a dust particle in a room, or heating in a room, or cooling in a room is turbulent diffusion. It is not Brownian diffusion, okay? And that's where you see the power of hydrodynamics. Now, so let's try to estimate the diffusion of cold air from air conditioner. So we need to introduce a new term, which is U dot grad theta, which is diffusion by the velocity field. In fact, it's quite straightforward. This temperature is advected by the velocity field, right? It's just carried by the velocity field. And this U is a hydrodynamic velocity. It is not a molecular velocity, okay? And now it turns out, we may ask, is the nonlinear term bigger or the diffusion term bigger? So which is bigger among the two? So we can do the estimate. So U dot grad theta by kappa grad square theta, U by kappa. U for right now for this estimate I am using as a 0.1 meter per second. L is 1 meter. Kappa is 10 power minus 5 meters square per second. So its ratio is 10 power 4. This is a typical scenario in atmosphere. So you see the nonlinear term is bigger than the diffusion term. So I should estimate time by equating these two, this term, this one and that term. Now if I do it, what do I get? Theta by T, it is U, the U is here, theta by L. So time is L by U, which is 1 by 0.1 meter per second, is 10 seconds. So it takes around 10 seconds for air conditioner cold wind to come to me. Of course, this is hand waving. I mean, this 0.1 meter could be lower or bigger and so on. But this is a general idea. The turbulent diffusion happens because of the hydrodynamic. This U is playing a big role, and it's a new physics. Okay, so and is, by the way, I use only one scale here, but this diffusion process involves many smaller vortex. Right now, please do not think that I'm using only one length scale L here. It is a many scales are involved. Many vortex are involved in this diffusion. Okay. Now, so this in this small article, I given this example as well as some more description. For example, I claim, well, I should not say claim. I believe that we cannot derive Kolmogorov theory from starting from kinetic theory. Okay? Like this energy flux is, I have not seen a very clear description from kinetic theory. Okay, it's a new description. Well, basically, it's a macroscopic description. Even if you could do it, why get to microscopic description? Okay, so that is what is the topic of this this article. Okay, now let's get to some more example. So second example is emergence of order in 2D Euler turbulence. Okay, so normally in statistical physics, it's assumed, it's again a conjecture, that any isolated system, okay, isolated system means there are particles or interacting systems like Ising spin, or it could be some system which is isolated from outside, hence the energy is conserved in the system. In this system, if you start with any initial condition, it will finally reach equilibrium. That's a conjecture. Okay, and there may be some exceptions, but people normally believe that it will reach to equilibrium. Equilibrium will be that energy will be equally distributed among all the molecules, or some equilibrium distribution, not necessarily equal distribution, but which does not change with time. Okay, it is unchanging in time. That is what is believed. But it turns out, I'm going to describe the Euler equation in a minute. It turns out 3D Euler turbulence obeys that law or conjecture, but 2D Euler turbulence does not. Okay, so that is my next description, and it's interesting, which we discovered last year. So this is the paper which is published, where we describe what I'm going to present in next 10 minutes or 15 minutes. Okay, this is another paper which you may refer to. Okay, so Euler equation. Okay. Now, so this is a equation for fluid mechanics, but without dissipation. So there's no viscous term here, or there's no diffusion. So it's assumed that the total kinetic energy of the system is conserved. Okay, so there's no diffusion, and this P is the pressure, so U is the velocity. So this is the Newton's law in some sense. This is a du by dt, acceleration. It is, I did not put 1 by rho. Rho is assumed to be constant, is 1. So it is a pressure gradient, which is a force. So acceleration is proportional to the force, and mass is 1. Okay, that's what we have. And we assume incompressibility. That means the velocity field is divergence free. Okay. Now we also don't force it. This forcing is turned off, so no force. Okay, F is 0. So no forcing, no dissipation. Now what do we? In fact, we can deduce some very simple, well, very interesting things from this. Since there is no dissipation, what happens to the entropy? Entropy in statistical physics or thermodynamics. Thermodynamic entropy. So you may recall, entropy is delta Q by T, right? Heat given, or so entropy increases delta S if we inject some heat into the system by, so the change in entropy will be delta S equal to delta Q by T, assuming constant temperature. Okay, so temperature is not very well defined for Euler flow. In fact, we don't need temperature for this equation, but let's assume that there is a constant temperature. Okay, or even if temperature is not, well, first of all, it's not defined here, but let's make T is constant. So since there is no dissipation, delta Q is 0. So if delta Q is 0, whatever T may be, delta S is 0. So there is no change in entropy. That means there is no change in order. Entropy is supposed to be a measure of order. So order does not change for this system. Now that's well, looks fine. Okay, if it's in equilibrium, then entropy will not change. But I'm going to show you that system shows variable change in, well, different order at different times. Okay, so even in 3D and 2D, so this thing is certainly not true. Well, now I'm giving a very intuitive description. Somebody may say, well, I'll come up with a new description of entropy for Euler flow, which is constant. Okay. Now, I mean, okay, I want to think simple. I'm just going to say entropy by visual order. Something has a very nice structure that has more order than something which is random. Okay, so that is what I'll say. Order will change with time. Now, so this has been stated in Landau's book. In fact, all textbook will tell you that delta S is delta equal by T. So for Euler flow, the entropy is constant. Okay? But as soon as I put viscosity, entropy will change. Okay? But I'm going to focus on Euler flow. So there are very famous and very competent physicists have worked on this equation, Euler equation. T.D. Lee, who is a Nobel laureate, he gave T.D. Lee and Creighton, Robert Creighton, they gave equilibrium solution of the Euler equation. Okay, so so there is a solution. Of course, we say that things do not change with time. Now the derivation is okay. I'm just going to give a very simple derivation. Their derivation is a bit more complex and more general, but I just want to give you a glimpse of the argument. Now, so the velocity field U for Euler. So this is a velocity field of not the molecules. This is the velocity field of the Euler flow at two different positions, R and R prime. Okay, if it is in equilibrium, then we say, well, it is uncorrelated in time and space. Okay? So this is a delta correlated R minus R prime, and its magnitude is U squared. So dimensionally it is U squared, and it is uncorrelated in space. Now, from this, if I do Fourier transform, this is a Fourier transform. So Fourier transform of a correlation function is energy spectrum. Okay, so this will give is a modal energy of a given wave number k, Ck, and the Fourier transform of a delta function is constant. Okay. So from this immediately you see that energy of a mode will be constant in time and space. Okay, so that is what is equilibrium solution. Energy is of every mode will be same. This is like equipartition. Okay, so you can easily see from the top equation that energy will be equipartition in equilibrium. Okay, and from this, so energy per mode is constant. In 3D, because number of modes is proportional to the area of the sphere, it is k squared. Is k squared, and in 2D is proportional to k. Okay, so this is a prediction. Of course, T.D. Lee and Creighton, they had introduced, they did realistic calculation, more realistic calculation. This is not much of a problem. They introduced helicity and so on, and they got a formula which is more general than this. But for our talk, this will suffice. This is okay. So energy should be proportional to k squared. This is called modal. This is a one-dimensional energy. The energy in a shell. Okay, so energy in a shell. It is proportional to k squared in 3D, and it is proportional to k in 2D. Okay. Now let's see whether we get this in a simulation. Now what we do is, this is in our earlier paper, the archive paper. We start with white noise initial condition. Okay, we start with the condition, initial condition which is uncorrelated in space. Velocity field is uncorrelated. Okay, it's possible to do it in computer simulation. This is done by our code called Tarang, which I didn't put it here, but I didn't write it the word. But the Tarang is the code which we used, which enables us to start with a random initial condition, and we get this random velocity field. Okay, so it turns out initial condition itself is random, and it remains random. Not a surprise. That's what happens. And it turns out if you look at the distribution of the velocity magnitudes, so here you can see that there are some large velocity fields and tiny velocity fields here. These are velocity field, huh? This is not molecules. Please keep in mind. So for every gate point, we have velocity field, and we do a PDF, it's Maxwellian, and it turns out the energy Ek by k squared is flat in this band. There's some very well. Just focus on the blue line, okay? And this is telling us that Ek is proportional to k squared. This is the Creighton prediction, which I don't want to describe here, deviation, but focus on the blue line. And energy flux, which is the important quantity which I talked about for Navier-Stokes, that is constant, but it is zero. Okay, this flux is zero. What does it mean? So there is no energy going from large scale to small scale. Okay, this phenomena, everybody has same energy. It's like in some sense the communist system where everybody has same money. They may exchange, okay, you take my bread, you give me something, okay. Ultra communist system where they just exchange things, and but they have normal same way of same standard of living for everyone. So there is no transfer of money or transfer of energy from one unit to the next. Okay? Now let's look at non-equilibrium solution. Okay, now this is interesting. Now we, instead of starting with the random initial condition, we start with vortex initial condition. Okay. Now this is a cut. Okay, this is not a 3D. This is only a cut. So we have 3D box, but I make a cut, horizontal cut. Okay. And these are vorticity, the color coding. So you can see that there are 4 vortices, well, 2 cyclone and 2 anticyclone. So these are t equal to 0 initial condition. And we let go. After significant amount of time, like t60, the velocity field becomes random. You can see this is random. Okay. Equal, well, same random as what we showed, what I showed you in the last slide. So things do become random, which is nice. Like the statistical physics conjecture, the system will thermalize with whatever initial condition you start with. Start from here, I become random. This is a work by Chikolovas in 2005. And if you look at the energy spectrum, initial energy spectrum was dot, because the vortex has a energy only in one wave number, but it distributes. And at t equals 60, we get basically k squared. The blue line is k squared. Okay, some variation here, but it's proportional to k squared. And the flux in the final state is 0, except some fluctuations here. I don't know whether t equals 60 is good enough. If you run it for longer time, these fluctuations do tend to come down, but there are fluctuations at large wave numbers. But on the whole, we are safe. It is reaching equilibrium. 3D is okay, not so interesting in some sense. Okay. Now, I think I will not get to that part. So this connected is arrow of time, but I will skip this part. Time is running short. Now let's look at 2D turbulence, 2D Euler turbulence. So instead of working in 3D box, I work in 2D square. Now we start with 3 initial conditions. Well, I just want to make a remark. If we start with random initial condition, then I get to that proportional to k. So random initial condition, like white noise initial condition, okay, uncorrelated in time, in space, that initial condition leads to equilibrium. No problem. But it start with ordered initial condition, like here we got 11 by 11 pairs of cyclones. Okay, so this is a lot of thing. Here we get 3 Fourier modes. So this initial condition, we just take it from me that we created by different choices of velocity field. So 3 different runs: run A, run B, run C, and okay. So I should have changed my slide. So we have better runs. Well, basically phenomena is roughly the same. That we run it for longer time. Okay, that's what I wanted to say. Now it turns out that this vortex condition gives you one nice cyclone and one nice anticyclone. So something going counterclockwise is called cyclone. If some going clockwise, this one is called anticyclone. Okay, that's a phenomenon. That's a terminology. That's the word. Now here we get cyclone anticyclone pair. Here we get 2 pairs of cyclone anticyclone. Okay. Let's sorry, 4 pairs. 4 pairs. 1, 2, and the 4 of them here. Okay. Now here what we get? Here we have shear layer. Shear layer is the velocity field is along positive x and velocity field is along negative x. So this is shear layer. So different initial conditions are giving different final results, and it now you, I mean, trust me that these are steady states. That means these structures do not change with time. There are some fluctuations, but we are getting basically structures which are not changing with time. Now, these are not random velocity field like what we got in 3D. I will show you that these are not equilibrium states. These are non-equilibrium states, that's what we claim. These are not equilibrium states in the sense that there is a these are energy transfer across modes which are significant, and there are different structures depending on the initial condition. So this is very different in 3D. Okay. Now, so we can look at the energy spectrum. Now, so this is of course not K. 2D has, we need to think of entropy is a important ingredient. Now, Crittenden prediction. So my simplistic argument is not working here. Okay, so please keep in mind that argument is not incorrect. That is for, if you start with white noise, I get that. But if you start with some entropy sitting in there, then we get this K minus 1 by K. At large wave numbers, but this thing, so Crittenden prediction is the black line, which I didn't state it here for simplicity, but the Crittenden prediction is black line, but at small wave numbers, the Crittenden prediction simply does not work. Okay, so in this band, in fact for blue line, this part is not working. So wave number 1 to 40 for blue line doesn't work. Okay, we look at the energy flux. It is not zero like 3D, and the energy flux is non-zero. It fluctuates quite a bit, but these are telling you that the energy, so this is not like system where everybody has same energy or things are not changing with time. It is changing with time. Okay. For large wave numbers, there is certain equilibrium. This part is in equilibrium, and this part is non-equilibrium. Okay. So it's interesting that we can have a system where some modes are in equilibrium and some modes are non-equilibrium. Well, in some sense, our population, some rich people are having more dynamics, and poor people are some kind of in equilibrium. You know? So that kind of scenario, multi-scale scenario, seems to be happening here. Now we look at, these are not very difficult equation, but I just want to tell you this part. So we look at energy change with, so for given wave number K, shell, not wave number, shell, dk by dt is energy going into that to the shell, tk. Okay, so this is called nonlinear energy transfer. Now we find that we compute them for 3 different runs. Now it turns out for Hamiltonian systems or for isolated systems, in standard statistical physics argument, you can say that this tk will be 0. There won't be any nonlinear energy transfer, right? I mean, they said in equilibrium, the people are exchanging small energy among themselves, like in a ideal system where everybody has the same money. Well, I won't say it's ideal, but anyway, some system that is tk is 0, and energy will not change with time, right? The ek will not change with time. But in our system, we find that we plotted this dek, both this quantity left hand side and right hand side. Okay, so dashed one is tk, the dashed black line, and the solid line is this derivative. Okay, so there are two things. They are equal, of course, but they are large fluctuation. So 10 power minus 2, which is significant. I mean, it's not like 10 power minus 6. And there are 3 different wave number shells. Okay? Now, for all these 3 runs, we have significant fluctuations. That means it is a non-equilibrium system. Okay? That's what our claim is. So this is not the standard statistical physics system where things are not, well, it is a non-standard, and this system is not thermalized. It's out of equilibrium, and that's what we argue. Now, order. I wanted to say about the order. So we phrased a new thing called hydrodynamic entropy. Okay. Some people have written about this, but I think we are trying to explain this intuitively as well. So thermodynamic entropy. So well, I think I will not. I already have around 5 minutes. So thermodynamic entropy, everybody knows. So this is for a system in equilibrium. Okay, a gas in a Brownian motion. That's what you should think of. Brownian gas. So entropy is a function of temperature, volume, and number of particles. There's a formula derived by Boltzmann, Gibbs, and so on. And this captures a microscopic process very well. Here it is in equilibrium, so there's no energy transfer, no energy flux, and so on. But hydrodynamic entropy, when we have this vortex, like in atmosphere, or for perfume diffusion, which I described, or for air conditioning diffusion of cold wind, So how do we describe order in such system? It is non-equilibrium, but it's changing with time. So we said, well, for a given snapshot, this is a snapshot. So I have velocity field at different position. So I do Fourier transform. Okay, so I do Fourier transform, and I look at energy for a mode, Fourier mode, EK. I divide that by total energy. Okay, and that is probability for me for wave number K. Okay, abstract definition, but PK I need probability, but it's a multiscale physics. So it's a well, PK or probability of occurrence of wave number K is given by EK by E. Okay, so that's what we say. Now after that, we use Shannon formula. Shannon is a very famous electrical engineer who revolutionized the signal processing world. Okay, so he gave a definition of entropy for a signal. Okay, and we use the same formula, Shannon formula. S is minus pk log pk, but pk is given by this. Okay. Now I'm going to use this formula, which given velocity field, I can compute it. Now, of course, you can see there's a multi-scale description, and also, interestingly, for thermodynamic description, this one we do ensemble average, right? This is entropy is defined e to the power minus beta e in statistical physics. E to the minus beta e sum or all configurations. Okay. None of it. Well, we don't do it here. For a given snapshot, I can define entropy. I don't need ensemble average. Okay. So that's another definition, a difference. And this is microscopic order is captured by this definition. Okay. Now let's look at what happens for 3D Euler flow. So we have, I'm going to look at, by the way, and let's look at it here. So I start with this initial condition and I reach here. So I can compute entropy for this. Is ordered, entropy will be small. Okay. In fact, entropy is very close to 0 for this. It's ordered, no? So pk log pk. If energy is focused only on single wave number, you can see here. If pk is 1 and 0, pk is 1 for one wave number and 0 for otherwise, entropy will be 0. Okay, pk log pk is 0. But here, of course, energy is distributed among several wave numbers, so it is non-zero, but it is small. And we reach equilibrium state, energy is maximal. Okay, we can compute this for this configuration. It is a maximal entropy, and it's increasing. Okay. Great, that's what we get to in 3D. So 3D is entropy is increasing. You may say that, well, this is consistent with what we do it in thermodynamics. Entropy should increase, right? I mean, people say entropy should increase. Yes, of course. Entropy for hydrodynamics too is increasing. But in 2D, let's look at entropy for these 3 runs, run A, run B, run C. In the beginning, the entropy can increase, okay, for run A, this one, but then it starts decreasing. So from this point onward till here, entropy is decreasing. Okay, for red curve. Blue curve, which is run C, entropy is again kind of fluctuating, but it can be lower than the initial entropy as well, or I can claim that for a period of time, entropy decreases in an isolated system, which is not connected with the heat bath or connected with the outside world. That means system is getting more ordered. So this system is more ordered than this system. Initial condition is less ordered, final condition is more ordered. Okay? It happens in hydrodynamics. Okay? Now this looks counterintuitive to law of thermodynamics. Well, thermal entropy is not changing here. Okay, please keep in mind delta S is 0 because there is no heat flow. Okay, but hydrodynamic order, which is in fact what we see is probably hydrodynamic order. When I look at the atmosphere, I look at microscopic description or cyclone, which is there in Bay of Bengal. I'm looking at hydrodynamics. So order can decrease in hydrodynamics, especially in 2D. Okay, 3D of course it didn't increase, but 2D or even rotating systems it may happen. Okay? So the problem is in fact turning off the viscosity. Okay, in rotating system, if you turn off the viscosity, there is no guarantee that code will run. So that's where this investigation is difficult. Typically, the code tends to blow up if there is no reciprocation. Okay, so so order to disorder, is it true or not true? For isolated system, thermodynamic entropy increases with time, but hydrodynamic entropy can decrease. It happens in 2D. Okay, and so I think this has some window for self-gravitating system. Okay, self-gravitating systems could be isolated, and it can entropy can increase for such system. For example, you see now clumping of matter in star formation. You can think of this atoms of this, not atoms, this packets of matter are collecting together. Is entropy, well, I mean, this is, by the way, is somewhat unsolved problem. Entropy of a self-gravitating system. Okay. Now, but I think new definitions may help us get a better insights. Now, entropy of the universe, so in Big Bang theory or oscillating universe, when universe is going from, well, in the Big Bang theory, universe is supposed to expand, then collapse. It's not clear that happens in the universe or not, but it is one model. While collapsing, the system will get more ordered. Well, it goes to the point. Then what happens to the entropy? Of course, there's some ways to go around it. In fact, some books go around it saying even if it is collapsing, the entropy is increasing. Okay, but maybe new definitions may give us some better insights. Okay, so I'm putting my neck out. That's what I'm doing it here. Okay, Professor Sandhuvalam, can I take 5 minutes?
Another sure,
small,
sure.
nice video I want to show.
Yeah.
I'll just take 5 minutes, then I'll.
No problems.
So arrow of time, I think this is my favorite. So this again connected to statistical physics. So arrow of time is basically defined. Well, there are many ways to explain arrow of time. I'm going to tell you what is arrow of time. Okay, in few minutes. But normally, say entropy increase will define the arrow of time. Okay, so let me just. It's very simple 5-minute presentation, and I just want to give you a glimpse of that. So fundamental laws like gravitation is symmetric under time reversal. Okay. So what do I mean? So let's run a ballistic motion. So there's a projectile going from left to right. Okay, right? Assume no friction. It follows a parabolic path, right? Now, imagine that I reverse the velocity field at the final position. I reverse it here. So velocity field will be reversed. And what would be the trajectory? The trajectory will be here. You just play it backward. I just took a YouTube movie, which is below, and I just played it backward. And this backward movie follows exactly the same trajectory. Okay. Now, if somebody played this movie, backward movie, then would you say that it's a fake movie? Okay. Because you see, in real life, of course, real life without friction, this trajectory of projectile will be exactly like what happened from in this movie. It just went backward. So, if somebody gives you a backward a movie which is played backward or time reverse movie, and somebody made a real picture of the projectile motion which is going from right to left, you cannot differentiate. Okay? Without friction, the system is identical while going forward in time and backward in time. Okay? Friction breaks the symmetry. Friction will deviate it from parabola, and then you can figure it out. This is easily, you can just think about it, you'll find it. Okay? Now, but in real life, of course, real life is a friction. Okay, now let me get to this. So here, actually some of it is, I believe, just making a phenomena more complex because of your arguments. Now, what is argued in normal, what is argued in by famous physicists? Well, laws of physics are symmetric under time reversal. most laws. Okay, there's one law which is not, but most laws are symmetric under time reversals. But then world is not symmetric under time reversals because see, I am growing old. Then what is causing this asymmetry? Now, what we see in real life, it is going in one direction. I do not see this thing going backward in time. I think it's, of course, if you look slightly carefully, it is bunkum. I don't like this question. In fact, the question is ill-posed. You see, when I'm growing, well, I'm living right now. So to go first I'm breathing in oxygen inside, and CO2 is coming out of from my nose, right? What is meant by time reversal? Should I breathe in carbon dioxide and remove oxygen? Well, that's what we need to do, no? I mean, to reverse, everything has to be reversed. So it's a pretty much ill-posed question, according to me. Okay, I mean, I think if you look deep down, there are too many assumptions about this isolated particle, point particle, and based on it, we try to say, well, why is world going in forward in time? World is more complex. It is not made of point particles. There's friction all the time. Okay, friction, according to me, is real. Friction will happen in all systems because of multiscale phenomena, which is part of this paper, which I'm going to cite it in the next slide. So it turns out we can explain this by fluid mechanics very easily. Okay, even for Euler, we can explain arrow of time very easily. Okay, so okay, now this is a nice picture, nice video I want to show. In real life, this is what happens. Okay, this is forward, right? I mean, this is very clearly. Let's play the movie backward. Now we can easily figure out why it is going backward. Of course, Amitabh Bachchan is not a point particle. That's one simple example. Okay, okay. So there are a lot of, I think, assumptions which go in. That's a fundamental problem of fundamental laws. These are based on very idealized assumptions, and that simply doesn't work for real life. Okay. Anyways, my idea is that this is the paper where I say hydrodynamics, there is a natural arrow of time because energy is flowing from large scale to small scale, and that defines arrow of time. Okay. Now this is a paper which came out in 2019, and there's of course friction. In hydrodynamics is a friction. That also helps you to get to this, and this is argued in this paper that if I play this movie backward in a hydrodynamic turbulent flow, by visually you may not be able to say that this movie is played backward, but I can compute the energy flux. Forward direction energy flux will be positive in 3D, but reverse movie will be showing negative energy flux, and from that I can differentiate the fake movie with a real movie. Okay, so this is argued here. So I wanted to say that these are some interesting problems which can be argued and discussed in multiscale framework. That's the theme of today's talk, and so I thought I will bring it into. So arrow of time can be explained using direction of energy transfer, which is a multiscale phenomena. Okay, and useful when entropy is not defined. Like for example, well, I just didn't have time to say it, but normal arrow of time description is where thermodynamic entropy increases with time, right? The compressed gas expands because entropy is increasing, and that is the forward direction. Okay? But for Euler system, we don't have entropy. Even for Navier-Stokes equation, defining entropy is an issue which we are trying to figure out. Navier-Stokes is more complicated. Let me just put it right now that way. Okay, so there are more examples like phase transition is multiscale phenomena. This is what many, well, Landau, Wilson, there are many Nobel Prizes for that. Temples, well, very nice. South Indians have more magnificent temples, and this is multiscale, right? I mean, there are structures within structures. Okay. Trichy has a very nice temple very close by.
Yes.
And city structures, Paris, so you can look at Delhi, there are multi-scale big colonies, small colonies, and big structures, small structures. So these are society. This is a class society, and we have all such structures. So summary: many phenomena world are multi-scale. I gave some examples, concrete examples, where I showed that atmospheric diffusion is multi-scale, and hydrodynamic model is able to explain it. Okay, which is not Brownian motion definitely does not explain it. Isolated system may evolve from disorder to order, and the concrete example is 2D Euler flow and arrow of time using energy cascade. These are some concrete examples. Okay, so I'll end here, and I'm happy to take questions.
Thank you, Professor. Thank you very much. So, sir, there is a question in the chat box. Are you able to read, sir?
Okay, so I think I will. Okay, I go to the chat box.
Yes.
So where is the chat box? Actually, I'm normally in
right,
a Zoom. I'm very used to Zoom.
Right
chat box.
Bottom.
Chat box.
Yeah, near the number of fellows, you can see chat with everyone. The first one is information. Second one is number of persons.
Could somebody read? Could you read the chat? I'm not able to get to the chat box.
Sure. Or Prasad,
sorry,
can
I'm just like
Prasad, can you?
Chat box is here. I got chat. It's to the right.
Yes, sir.
Prasad
Yes,
says.
Yeah.
Okay.
I'm sorry. So, Prashant, if you want, you can ask, or I can read. Okay, let me read. Arrow of time. Time is considered to be a scalar entity, but it's possible to think of a situation, maybe in and out situation, which you may have, where time needs to be considered a vector entity. No, time is a scalar entity. That's not an issue. So whether time, so by the way, time going negative is, I'm not saying time is going negative. So I think you are thinking of, so just think of 1D motion, okay, 1D motion. So random walker is going forward by some steps, then going backward in some steps, okay, 1D motion. So time going backward is, you can run, for example, a diffusion, compressed gas is diffusing, right? That is forward. I can play the movie backward, so time will flow backward. That means this expanded air will come to a compressed state. Okay? That is the scalar time. Time is just going backward. So T is going from T final to T0. It happens sometimes, okay? For example, pendulum. Pendulum can go forward and backward with equal probability, right? Frictionless pendulum. So you can think of going from left to right is forward and right to left is backward. So some idealist examples are going both ways. Okay, but that does not happen in real life. I hope I'm clear. We don't need to make time as a vector.
Okay, sir. Thank you so much, sir.
Thank you.
Sir, about the cyclone and anticyclone pair, sir. So is it needed to like it's necessary to get cyclone and anticyclone pair also, or there can be cyclone pair also? Is there any observation?
Yeah, good question. No. So conservation of for vorticity. Okay, in Euler flow, entropy is sorry, not entropy. Omega is conserved under periodic box. Okay, so there we will get cyclone and anticyclone in Euler flow, but as soon as I put rotation, then cyclone is more than anticyclone. Okay, that's what happens in atmospheric flows. You get more cyclones in the northern hemisphere than cyclones. So Euler flow, yes, they're equal in magnitude, in the sense positive omega, sum it up, this omega will be 0. But for rotating flows, that is not the case. Omega is not conserved. Integral of omega, curl of u, okay? Is it okay, Prasad?
Yes, sir. And sir, is there any observation that if there is cyclone anticyclone pair, the distance between these two pairs do vibrate like atoms in the molecule? Like a very rough question.
No. Well,
not like.
No, it's a very good question.
Yes.
So it turns out the equation for okay. So you can think of point vortex. okay, point vortex, which is like delta vortex, like that has same equations as Boyle-Sauvert law. So curl of omega is 0 for incompressible flows, and del dot omega is 0. Okay, curl of omega is the delta function. Sorry, curl of omega is the delta function, and del dot omega is 0. So say the same as del dot B is 0, and curl of B is current. Okay, but the solution is not the same. Okay, solution is slightly different, but there are analogies. If you, it turns out we can make this connection. Let me get it right. The vortex is the same sign, they attract, and what is the opposite sign, they repel. Something of that sort. Okay, right now I don't have in my head, but there are analogies which can be made. And Boyle-Sauvert law is used for time evolving delta vortex. Okay, so your thought is in the right direction, but there are some differences. For example, this vortex anti-vortex, vortex pairs go in a straight line rather than going in a circle. This is there in Bachelor's book, the derivation. So the vortex, they do not, the distance does not change and this is going in a straight line. But vortex and anti-vortex go they rotate around each other. Okay? So these are done, I mean, there are math calculations which are reasonably complicated, but it's all doable. Okay,
Okay, sir.
You can look at Bachelor's fluid mechanics book.
Okay, sir. Okay, sir. And sir, like I think already you explained. So there is also like a flow of some energy or some field from one pair to another pair, right? From one cyclone to another cyclone or anticyclone. So is it
Yes,
so?
there is a transfer, and
So
there could be back transfer. It's a complicated process. Yes, there are transfers.
okay, sir.
In such systems, there is no okay, everything is done now. Stop. No, not that way.
Okay, sir.
It's
So
very dynamic, and
okay, sir.
yeah.
We can't predict that it will it will lead to.
Actually, there's no one law. As I showed you, 3 different initial conditions led to 3 different final states, right? So I cannot make one law that it will get there, it will get there. These are issues with non-equilibrium systems.
Okay, sir.
We cannot say that, well, this is what is going to happen finally.
Okay, sir. Thank you so
Change
much,
the
sir.
initial condition, you may get a very different result. But yes, there are laws. As I said, cyclone vortex anti-vortex pair go around each other, and things like that. Okay.
Yes, sir.
Yeah.
Thank you so much, sir. Thank you.
Thank you.
Students, any other question? You can also write in the chat box.
Okay, I may ask one question. So, if there's a movie buffs, which movie that I took a snapshot? I took a video bite of a movie.
Yeah.
Which movie that is?
I don't know if these people watch a Hindi movie.
I see. Okay.
I think Amitabh Bachchan movie, right?
Is Amitabh Bachchan movie, but which movie is the question?
I think students.
Yeah, but it's an old movie, of course. Not a modern generation, but yes. Anyway, let's skip that.
Yeah. Students, do you have any other question, clarifications, or doubts? There are no more questions, Professor.
Yeah. Yes.
Okay. Yeah. So this hydrodynamic entropy is a new concept developed by your group, or?
Yeah, so I would say, so I can just say this, for boundary layer, there are some papers which use the same formula for saying that their structures can be defined that way. So this formula exists in 1 or 2 papers before us, but I think we are giving a kind of clearer enunciation of this formula. So we can claim that at least if you are not the first to write the formula, but we are probably one of the first to explain its power.
I see.
That would be more modest as well as immodest combination of the two.
And it explains many situations, right?
Yes.
Okay. Students, do you have any further clarifications? Okay, Professor, there are no more questions. So,
Yes.
Yeah, since there are no more questions, I would like to conclude the session by thanking Professor Verma for giving a very wonderful talk. Okay, a very recent topic, and he has done a very good job. Very good, many discoveries in this area of research. So, we are very fortunate to hear your findings, Professor.
Many
you very
thanks, Professor Divalan, for your kind words, and thanks all of you for coming and listening to me.
Yeah, and I will write to you the other details by email, sir.
Excellent.
Okay,
thanks again for the invitation, and thanks for the good opportunity to discuss. Okay, bye.
Thank you, Professor. Bye.